All right. So, welcome everyone to yet another lecture of 2DM3 in this wonderful year of ours, 2020. If only we all had 2020 vision. Um, so let's try to get everyone ready for the midterm on Tuesday, October 6th, I think. So let's go over some material and see how that goes. As usual, I have the chat open over here, so let me know if you're going to talk about anything in particular. So I do. So from those of you who are here, maybe maybe we can take a poll. Yeah, you don't expect too many word problems. Yeah, don't do that. So right here, notice it doesn't say 3.1, so don't worry about word problems. Um, uh, who would like to just walk over the slides and I can type over them using using my handy dandy screen brush. All right. I can do this if you like that. Or who would like me to actually write CalcCheck and hope it works? So let's would people prefer live coding and all the possible messiness that comes with it? Or what would you prefer? Okay, so we have one person that said live coding. Can you guys just like that one person, and then we'll see how many likes that one comment gets, or just keep spamming me with live coding. All right, okay, all right. So it seems live coding is the way to go. It has a lot of likes. Oh, you like to hear my thought process. This is good to know. I appreciate you letting me know, because now I'm more motivated to make mistakes. Not on purpose, but apparently so. I will keep the slides on. That's fine. All right. So it seems like the majority of people. I'm like the chat is over there, but you're over here. Anyhow, the majority of people would like me to continue having to do live notebooks. So let's do that. And we can talk about a lot of stuff. We can talk about a lot of stuff. So I do have the chat. Please ask me there. If you don't want to ask verbally, that's fine. But just let me know what you want to talk about. So I opened up a bunch of notebooks, and we can tackle things as you like. Not a big concern. So I'll just quickly over what the plan is for today. So we're going to talk about what an order is, right? Don't worry too much. We'll get into that in a moment. So this is 7.2. 7.1 is supposed to help you get ready for the midterm. All right. And we're just going to wrap up some replacement stuff from yesterday. So nothing really new. We're going to wrap up replacement. All right. And we're just going to talk a bit more about implication to get you comfortable with it. And maybe we can do some induction if you like. Okay. So that's the plan essentially for today. So here's a bunch of information about the midterm from yesterday. Feel free to look at it, and slides will be online. Yes, 7.2 is due next Thursday and not on the midterm. Somebody laughed about that. So if again, if you're seriously interested in finding the deep relationship between inference rules and theorems, you could look at this book, Gödel, Escher, Bach. It's a delightful book with lots of art and stories. Like it's a dialogue between Achilles and Tortoise. Right? This is a Zen dialogue. Right? What is Buddha? This mind is Buddha. Yeah. So yeah, lots of stuff. Different. So in our class, we're using the logic system E. This book uses many other logic systems to make things easier. So E looks a bit hard, like it has Leibniz, it has a lot of complicated stuff, because E is supposed to be useful. E for equational logic. This book starts off with really simple ones that are not that useful, but they just show you the idea of what a logic looks like and how you can use a logic and what does a logic mean. Okay, so when people say the logic or we use logic, ask them which logic do you use. There are many. Anyhow, so as we mentioned yesterday, rather briefly, and again, in case you don't want to read the book and maybe you don't know what's going on in LADAM, I have tried to explain here in the abridged notes the relationships between inference rules and our formulae, how they relate. Okay. The idea is that an inference rule takes theorems and makes new theorems. Okay, that's what inference rules do. It's like the successor operation. The successor operation takes a number and makes a new number. Okay, like for natural numbers. So that's what inference rules do. If you have a theorem up here, you get a new theorem down here. Okay, it's like addition on this side over here. If you give me two numbers, then you get another number. Okay, whereas the axiom Leibniz is a theorem, right? It's not a theorem maker, it is a theorem. So for example, this inference rule takes numbers and makes a new number. It's a number maker, but 19 by itself is a number, okay? So it's different levels, right? So you can think of them as being the same, but the inference rule acts it acts outside of the system, right? It's like you're looking inside the box, and the box has all your logic stuff, and then you can take a theorem and then change it and then throw it back in the box. Okay, so the inference rule is meta syntax, right? So the idea of meta is also covered here for various other things. So we've covered a few. We've used the word meta expression sometimes. We've used meta variable. We've used meta operator. So the idea is that this is something that acts above or beyond. Okay, ducks. So we saw some examples yesterday, right? If you want to apply this thing, right, you have to find the particular substitution you're going to use and actually apply it, right? And of course, there are particular cases. We see them as contextual rules, right? In the context that E equals F, I can replace every E by an F, okay? And likewise for implication. So let's maybe it's a good time for an example. All right. So let's see. So let's try an example somewhere. So here's an example. Let's just look at that. All right. So x equals 3, and I'm going to replace x plus 2 equals 5. I know that 5 is the same as 3 plus 2, no problem. And then substitution, right? Substitution tells me, hey, everywhere I see an x, let me just call that z temporarily. And then over here, I saw a 3. I'm going to replace that by z as well. And the reason that this is allowed is precisely what Leibniz says. Okay. Let's look at this again from a different perspective. Whoop. Okay. So let's actually use the knowledge that x equals 3 here, right? So where the implication happens on this side right here, we know, after the implication, we know that x equals 3. And this knowing that we actually know it is captured by replacement 384b. It says everything here can make use of this information, E equals F. In particular, you can replace every E by an F, right? So when we say if this, then that, and in the then clause, I know everything is true in the condition, that's formalized by the replacement rule. So these replacement rules or contextual rules formalize or encode the fact that we have local knowledge, okay? In comparison to the inference rule, which requires global knowledge. It requires x equals y always for any variables. X equals y must be a theorem. No matter what values are chosen for the variables, x equals y must be a theorem before you can apply the rule. Whereas in axiom Leibniz, I provided E equals F in a state, locally. There is some choice of values for variables that makes E equals F true, then I can use this substitution. So that's the main difference. One is global, it lives outside the system, it takes theorems and makes new theorems. The other one's inside and speaks about local choices. Right? So let's actually use that. So here's x equals 3, and I want to replace it. X plus 2 equals 5. I just want to say, let me replace x by 3. And this is called replacement. Now, who thinks this is going to work? All right. So here's the slide. Okay, so it won't work directly. because the calc check doesn't have the necessary high order matching. So if we try it, it crashes, right? Instead, we have to make it clear which variables we're going to substitute. So let's say x equals 3, and here I'll replace x by a new variable called z. Okay, and I'll say z becomes x. Okay, and of course this is just substitution. So let's check that. Great. Now I can apply replacement. Replacement doesn't say this though. Replacement says x equals 3, and you can use the local knowledge. The local knowledge is that I can replace every textual substitution not by x, but by 3. Okay, and then I can do substitution to simplify. Okay. Oh, could not justify. Sorry, this one should be. This is something we have to prove in this notebook. 3.84. B. Da. We have to prove it in this notebook. This is the problem of doing things directly. Still not. Okay. Well, this is quite unfortunate. I'm in a notebook that won't allow this to happen. I will not give up. Let me just go to my own notebook. Schroeder. Let's go here. Tests, not calc. Sorry about this. Should have probably prepared ahead of time. And V. Open import prop logic all. Okay. This one should now be calculation. Okay. There's just never enough. Sorry again. One moment. Which one do I want? Apologies, I have too many notebooks opened up at once. Go back to week 3. Conjunction. No, not that one either. I have too many notebooks at once. But I hope you believe me to some degree, even though I do not have the appropriate notebook opened up. Oh. All right, maybe I'll just stop checking things, and then maybe you'll believe me a bit. Sorry about that. Okay. So let's get back to this main notebook. All right. Are there any questions? I feel like I've caused some of you to be confused. We can do this one without replacement. Yes, you can. That is true. You can do it without replacement. I just wanted to show you how you could use replacement, and unfortunately, I failed to do so because it has to be proven here. All right. So we could do it in this setting. So let's try that again. V. Okay, so here, everything works if we use and instead of implication, because implication is not imported into this notebook and we haven't proven it yet. I apologize for that. But the idea is we have this local knowledge x equals 3, and we're just going to use it on the right side. We're going to use it on the right side, right? Try to use it actually, and then substitute. Okay. What was the difference between running replacement on the original equation and running it on the substitution? So you can't just call replacement directly. So this is the problem right here. If you look on the left side of the screen, you can't just call replacement because calc check cannot do it. So it's not a matter of reasoning. It's a matter of tool support. Calc check just can't do that directly. right? There's too much matching, there's too many expressions involved, and CalCheck can't figure out what you're trying to do. So you have to explicitly tell it, this is the subexpression I want to change, all right here, Z, right here, Z. So the point of the textual substitution is to make a pointer, a reference to where you want to make the substitution, all right? You might be able to use substitution in previous CalCheck notebooks. Sometimes I accidentally give you access to more theorems than you should have. But going forward is where you use substitution. Some of the theorems you've seen before can be proven much more easily using replacement laws. All right. Yeah. Okay. Great. All right. So here's a few examples, right? When you have this one, you have a Boolean expression and you want to replace it, you can use 351. 351 is specifically for Booleans. Okay. Here you have a value and you want to replace a value with another value. So here you want to use 384 substitution laws, replacement theorems. Here, this one is a Boolean and you can replace a Boolean with another Boolean, again, using replacement. Okay. So here's how you could do it. But the important thing to understand is 351 is only for Booleans. So I recommend you just learn 384. I recommend 384 all the way. For Booleans, it's not as effectual. Okay. Yeah. Every time you want to use 384, you first need to do a substitution, then apply 384, then do another substitution. That's like the rule of thumb. If you're going to do it, you have to pad it with two substitutions, one before and one after. Okay, ducks. All right, so replacement, this is 351. Again, I recommend you just pad with a substitution before and a substitution after. Okay. Padding with two substitutions is more general and it will work for more cases. All right. Here's another thing I want to point out. So notice you can use multiple hints. Here's one hint, and here's another hint, and then substitution, right? So some notebooks will allow you to do that. You can say and, right? So notice right here, this one says only one item allowed. So when we start letting you do multiple hints, you'll be notified. So this particular one won't work in this notebook. Right? You can also use a comma. But again, in this notebook, we're saying please do only one item because you're learning about substitution and trying to do too many steps can confuse the system, and even worse, it can confuse you. Okay. Alrighty. Okay. So I personally think so 384A is just 384C, but a bit weaker. So I think these four are really helpful to know. Like the 384s, I think they're quite helpful to know. In general, you will have syntax checking and not proof checking. Like almost always, that will be the case. You'll have syntax checking, but not proof checking. Okay, ducks. All right. And of course, remember we talked about having local knowledge. So remember the identity of equivalence is true. So replace P by P equivalents true, and then you can apply this one, and then replace P by true, right? So you use local knowledge again, but because the Booleans are special, you can pop off some parts of the equalities, things become easier, right? So P equals true, so you can replace it by true. This just contrapositive, flip it around, and then you get not P, that is P equals false, and so you can replace it with false. Okay, so and Shannon is just truth tables again. Right? Shannon says whenever you have a variable P, suppose P is true and replace everywhere you see it with true, or P is false and everywhere you see it is false. So let's take a break to prove a theorem. I feel like when we go too long without a theorem, I might need to make more mistakes. So here is a calculation. So what does Shannon say? Shannon says P with Z becomes lowercase p is the same thing as P and P with Z becomes true, or P negated and lowercase p becomes false. Okay. Well, that doesn't help. If only I could move this. There, whatever. So here's theorem Shannon. Command V. Proof. Okay. Why is Shannon broken?
In that last term, beside disjunction, it's supposed to be Z, it becomes false, not P becomes false.
Oh, is that what I wrote?
Yeah,
Z, so Z becomes true.
And then the last term after disjunction.
Or P. Not P and Z. Okay, thank you. That is still not correct. What is wrong? Right here. Oh, I got my parentheses out of whack. Okay, there you go. Okay. Sorry about that. So let's prove a stronger theorem. Let's prove this new theorem called strong Shannon. Okay. And the point of proving this theorem is just to give you guys an excuse to tell me how comfortable you are with prop logic. Okay, so here's a theorem called strong Shannon, and I'm just curious, can anybody tell why it looks true? Just intuitively, all right, or by looking at the symbols, can anyone tell why this is true? Somebody said you're replacing an and with an X. That's right. I'm replacing an or with an XOR. That's correct. But why does that make it true? Contradiction. Exactly. Notice right away I have a P and a not P, and those guys have a contradiction, right? So this, all right. So who knows? Oh, sorry about that. What theorem am I applying right now? Does anyone know? So which theorem am I applying right now? Boop. Does anybody see what theorem I've used or not? Oh. Does anybody see it? Distributivity of and over Noah. So that's not what I used. So try again. So this inequivalence disappeared. Where did it go? So this is some stuff you should be comfortable with for the midterm. How did I get rid of it? Where did it go? So what am I doing now? Alternate definition, yes. Excellent. Oh, that's not what it is. Nope. Right there. Okay. So let's put that in there. Great. Could not justify the step. Oh no. P and everything. Oh no, that's not the definition I was thinking of. We are thinking of different definitions. Let me pull up the list for you. Oop. Alternate says not one or the other. I am thinking of a different one, which apparently I did not communicate sufficiently well. All the way down. Oh, we did not prove that theorem. I am thinking of a theorem that we have not even proven. That can't be right. No. Let's try this one. Sorry about that. Let's try. So we could have almost gotten there, but that would require some more negations. Yes. So the intuitive idea is because P and not P is not provable. So that is the intuitive idea. But it would require a few more steps, and I can show you if you like. So how about who's interested in me showing you the remaining steps or not? I'm just curious. Boop. Who would like to see the remaining steps? Or should I leave this for you? Okay. So this one is clearly Shannon. All right. So that's that step. This one is identity of or. Okay, 2 more steps. This one is contradiction. No, why not? Here's P and here's a not P. Oh, this is contradiction and 0 of and. Okay, so we're not allowed to have multiple hints, so that's unfortunate. And then this one I'll just leave at the very last end. Okie dokes. So this one is a mixture of alternate definition, of equivalence, along with the initial definition of not equivalence. Okay, so just to make that clear, where is it? Theorem. No, sorry. So here's the first one. So we're right here. All XOR says one and not the other, or both. So let me just make it as a theorem. XOR. P not equivalence Q is the same thing as I have P or Q, and it is not the case. All right. And it is not the case that I have both P and Q. So if I use that theorem instead, proof, which apparently is not yet a theorem, if we try to use that one, XOR, then we make this an and, go like that, contradiction, and we use negation of false. Okay, this becomes and true, identity, and there we go. Okay. Oh, I have too many parentheses somewhere. Right here. Yeah. So there's the way to do it, and here's a little proof theorem called XOR. Do you want me to prove this theorem for you, or do you want to try it on your own? I'm happy for either or. Just trying to get you guys ready for the midterm. So let's have a quick poll. Who wants to prove XOR and who wants to move on? All right, so we have a lot of people who prove XOR, so let's do it together. Where should we start? How should we start proving this theorem? Okay. Any suggestions? Right side, yeah, sure. Or definition of n-equiv. So again, when you're not sure what to do, you can take the whole thing and transform it, or you can start with the complicated side and see how far you can get. So let's start with the complicated side, as was suggested, and see where that takes us. Okay, so here we are. What's the first thing? So the goal is to simplify. We just want to simplify. How do we simplify? All right. What is the simplest thing we can do? All right. De Morgan sounds great. So let's apply De Morgan to get a not P lower L not Q. And then let's pray, all of us together, that this will work. Something went wrong. Right here. All right. Okay. Okay. What should we try next? Somebody wants to try contradiction. That won't work. All right. So sure, let's try distributivity. All right. So let's do P or Q and not P. And let's do P or Q and not Q. What do we do next? What do we do next? Distributivity of and over this one. Okay. Somebody says, let's do another distributivity. All right. How about, since we have this theorem list beside us, does anybody see anything we could use in this theorem list? Does anybody see anything we could do right here, right now? All right. Absorption, capital absorption with a B instead of a P. All right, great. Absorption. So what do I have here? Does anybody want to tell me what I have here? All right. Does anyone know? There aren't that many options. So the inside are both positive, the outside is negative. All right. So I get these guys. All right. Not P and Q, P and Q. Okay, 344C. Okay, great. Not P and Q. Not P and Q. Okay, and what do I get over there? Not Q and P. Okay, great. What do we do next? So just by knowing it was absorption, like the shape, you know, I had a P outside and a P inside, and then I'm like, oh, that's probably an absorption. Just knowing that shape saved us a lot of time. So we didn't need to know the theorem, but just we knew it was an absorption probably. And so we look up at our absorption list and be like, oh, wait a minute. I don't need to do a lot of distributivities. Let me just do absorption. Okay, so absorption can be very, very helpful. All right, what do we do now? We're nearly done. I'm pretty sure that's what we were trying to prove. Yeah. So what's the next step? Yeah. So let's try the definition of an equivalence. E equals Q. Blah, could not justify. What? Two things are different when one of them is true and the other one is not. This, sorry, this is the alternate definition. Alternate. There you go. So, oh, all right. So that was a fun little theorem. Yeah, fun stuff. I would recommend trying to prove this XOR theorem again using golden rule, and just to get comfortable with equivalence and negation, because that is something you need to do before. I'm not sure if you've seen this. This might be somewhere. I honestly don't remember. I don't think you've seen this, so maybe I'll add this to the list, because I do like this definition sometimes. I almost never use it. Actually, sorry, this is the one I use almost always in my head when I think of XOR. So here's this one. Yeah, maybe we'll add it in there as 353b. So maybe we'll do that. 353b. Okay. So let me make a note of this, and I'll try to add it. Okay. Boop. Just let me make a note of this for right now. Okay. Add that in later. Okay. Somebody wants to do transitivity laws. Sure. So let's go back to the slides. I have those here. So let's move on from this stuff. So we've talked about implication being in order, right? You can order the numbers by 0, 1, 2, 3. You've ordered them, and you order them using size, right? So the size of a number determines its position in the order. So 0, 1, 2, 3, 4, 5, 6. If you decide to order the numbers, for example, by you order all the even numbers, then the odd numbers, you would get 0, then the next number. What's the next number? 2, because you're ordering the even, then the odd numbers. So it's 0, 2, 4, 6, 8, and then you finish all the even numbers, and then you get to the odd numbers. You could try ordering them that way. You could order numbers by divisibility, right? You can say 2 comes before 4 because 2 divides 4. You can say 1 comes before all the numbers because 1 divides all the numbers. So when you use divisibility, the first number is now 1. Every number divides 0. So now when you use divisibility as the ordering of the numbers, you start with 1 and you end all the way at 0. Okay, so you have 1, you have 2, and then what comes after 2? Well, 2 divides 4, it divides 6, it divides 8. So now you have a bunch of things stacked up. Instead of being one after the other, you can have a whole stacking. And then what does 4 divide? Well, 4 divides 16, and 4 divides every power of 4, right? And so now instead of being a straight line, you can have branching out in your ordering, right? It's like when you go to Wonderland, and instead of having one line to the ride, they have a line for rich people and a line for people who paid, and a line for the musicians, and the lines sometimes branch out. So it can be like that. Okay. So when we treat implication as an order, then the definition just says or is maximum. So P is less than or equal to Q means the maximum of P and Q is Q. Okay. So when we think of orders, we think everything should be at least in front of itself. If X is in front of Y and Y is in front of Z, then X should be in front of Z as well. And if two things are in front of each other, then they should be the same. Okay. So for implication, we say everything's in front of it, like everything is right in front of itself. So P implies P. If two things are the same, then they have to be in front of each other. If two things are in front of each other, they have to be the same. If P is in front of Q and Q is in front of P, so this is just a weakening of equivalence. This is transitivity again. So P implies Q and Q implies R, so P implies R. So somebody says, let's prove this transitivity result. Okay, so there are a lot. So we talked about division a moment ago, but equality is also a way to order things. So when you order numbers by equality, the first number is, well, there is no first number. It's just a big stack. 0 is equal to itself, and 1 is equal to itself, and 2 is equal to itself. So what's after? There is no after. What's before? There is no before. So this ordering is just put everything in a straight line. Let's group them on top of each other. All right. So equality is a very, very boring order. So for implication, let's prove one of these transitivity laws. Okay. So you have a notebook here on implication that you will work on, and it has some transitivity laws. So let's make sure I don't prove either of these. So here's 382 and A and B. So I cannot prove either of these for you. I apologize. I cannot do these transitivity laws for you. I am sorry. These are homework. So we can tackle other laws if you like, but not these two. These ones. Let's see which ones. So here's 382A and here's B. We can do C. We can do 382C if you like, because that one's not on homework. 7.1, yeah, so 7.1 is homework, and so I can't do that. But we can do 382C if you like. I don't see it here anywhere, so we can try doing that if you like. Is that what people would like? All right, let's do that. Okay. So let's prove. What are we proving? We're proving that if P implies Q, and Q is equivalent to R, then in fact P implies R. Okay. So do we start with the left-hand side or right-hand side? All right. So some of you will think there is no left-hand side, there is no right-hand side. And when we get to chapter 4, we will see that you can think of this as the left-hand side and that as the right-hand side. And you can start here and work your way down to here. Okay, so if you remember in last lecture, I talked about transitivity rules allowing us to put not just equals and equivalents on the left side of a proof, but we can also have orders on the left side. And that's why we care about orders. They let us do even more powerful proof techniques. But until we get there, we will have to do the whole thing. We will have to. All right, so what do we do first? What do you guys want to do first? What could we possibly do first? Does anybody know? So we could go and use definition of implication. And using definitions is great. That's what fold unfold is about. That's the whole point of fold unfold. You see something you don't know, you use the definitions, and you work from there. But this is theorem 382C. This is pretty late in the game. This is not an early theorem. This is pretty late in the game. So we have a definition of implications like 350. So from 356 or something, or 359, it's really early. So from there till here, we have about 20 theorems in between. So maybe we can use some of those 20 theorems. All right. Does anybody know? So here, let me show you a really, really quick one that will not apply. It will not apply because we don't have 384 yet. But if we had 384, we know Q equals R. So we can replace every Q by R. Okay. And so P implies R, right? So this piece is right here, and we are done by weakening, right? If you have two things, you have the first thing, right? So if we had substitution, if we had replacement 384, we could have done that, and we would be done right away. So that would be a bit cheating. So we do not have this, and so we can't finish that quickly. So we can apply definition of implication. There's nothing wrong with that. Which one should we use? There are multiples. Who knows which one we should use? Right. How do we know which one we should kind of use? So I'm using the one with ands because we already have a lot of ands right here. That's the only reason I'm using that. Okie dokes. So what should we do next? So we see P implies Q, and we see P implies R. Okay, not that helpful. All right. So what could we do here? How could we massage this massive mess? Does anybody know? Because it's looking pretty hairy. P implies Q and Q equivalents R, and P implies R. P implies Q and Q equivalents R. Does anybody have a suggestion? I am very super open to suggestions. More. I mean, yes, we could totally do that. What about if we used this other one? What if we used 359, right? So instead of doing it like that, we could do 359. Then it won't be as long. So this would be not P implies Q and Q equivals R, and the whole thing like this, or P implies R. So we could do the whole thing. Yeah. Here's a not 1 2 1 2 1 2 1 2. All right. Okay. And then what could we do next? Control Alt. All right. Timed out. Oh no. Definition of implication 359. That's what we used. Okay. So well, here's another implication. We can get rid of that. Okay. Here's another implication. We can get rid of that. Okay. So what can we try next? We could try De Morgan's. All right. So now we have no implications at all. All right. So let's see. We'll have not P lor Q lor not Q equivals R lor not P lor R. If we apply De Morgan. Okay. And then we can apply De Morgan right here and have and then not and not. Okay, we could do that. So 359, right? So someone's asking, is right here, sometimes called material implication. Okay. So now we have only ands and ors, and maybe things are a bit simpler. Maybe they're not. But does anybody see absorption anywhere? So absorption is our old friend. Does anybody see that? Who sees absorption? Who sees absorption? So let's get rid of this guy, or not P right here. Put that right there. So this not P, let's just bring it all the way over there. Okay. And remember, we have automatic symmetry and associativity. So can we apply absorption somehow? Ooh, something happened. 1 2 1 2 1 2. Oh, right here. Okay. Does anybody? Nah, not you. Okay. Yes. So, okay. So let's. What about this absorption? Does anybody want to try tackling this before we move on? So I'll go right here. Here's the absorption theorems again. Does anybody know which one we should use? If P is true, all right, then and not P is false, so this goes away, and we just have not Q. And if P is false, that whole thing disappears, and it's true. 344D is what we've been told. So the outside is negative and the inside is positive. So we have the outside and the inside. So we can simplify like this. Okie dokes. Oh, nope, that did not work. We've made a mistake somewhere. Sorry, that should have a not in front of it. Good thing we have CalcCheck. Somebody says not P or not Q. Yes, good. So what should we do next? Somebody says let's do distributivity of this one. That's tricky to do. So why don't we bring that not inside first? Okay. So why don't we bring in this not before we do that? Commutativity. Okay, so now that we have that, now we can distribute everything over that equivalence if you like. And we'll have not L naught Q or L naught P, L naught Q, or R. Equivales R, lower R, lower L naught P, lower L naught Q. Okay, so there we go. Now, I don't know about you, but if I didn't have calc check, I'd be worried. Is that really correct? There was a lot of symmetry I just did there. Okay. So everything is good so far. We have a not Q and a not Q. We can simplify those down. We have an R and R. We can simplify those downs. All right. So how do you simplify repetitions? You do that guy. So we have a not P, a not Q, and an R. And what do we have on the other side? We have a P, and we have a Q, and we have an R. Brr. And what's the last step? Does anybody know? Whew. That was a wild ride. Okay. Whew. Yeah. All right. Okay. So that was a wild ride, and luckily we finished it in time. And I was hoping to get a bit more on maximum and minima. So hopefully we'll post these online. But definitely I'll get to monotonic and isotonic next time. And I think maybe these will make it into the next assignment. All right. I'll post this particular calculation in the chat if anybody wants to try it out. But yes, if you found some of these steps to be too much, I recommend you try to find out what happened. So there's a lot of implicit use of symmetry and associativity there. Lots of implicit use. So something to be aware about. Those of you who have to go, thank you for joining us. The rest of us will stay and chit-chat. And all the best to everyone else on the midterm.